seminar and he asked me some questions. I remember he was pretty serious and asking me questions about, I was a fresh PhD at the time, so it was good to at least have one point of contact with Professor Ozisik. Of course, most of the heat transfer people have read his books, so used his books, so we knew of him from that perspective. But today, it's my pleasure to introduce Dr. Srinivas Garimella, who I've known for almost 30 years now, and is somebody I look up to from the heat transfer perspective. I've always admired his high quality work and his ability to solve problems, which is what he's very well known for, is actually solving real problems that affect our daily life. Many of the stuff that he's done is incredible, and he's going to share that with us. In terms of he didn't want me to talk too much about him, but that's how he is, but I'm going to do it anyway. He's been in many universities, but last 22 years at Georgia Tech. And he's received pretty much every award in the heat transfer and ASHRAE, ASME heat transfer and the ASHRAE areas. He's got the Memorial Award, which is the highest honor in ASME for heat transfer last year. In addition to that, he's also got the ASHRAE awards, the Ralph Teeter Award, and then of course he's been a co-author of 375 papers, textbook on heat transfer and microchannels, and in addition to that, he's given lectures across the continents, maybe not in Antarctica yet. Not yet. But with the global warming, it might have happened soon. But yeah, so without further ado, I'll let Dr. Garimella talk about his research and his contributions to heat transfer.
Thank you, Srinath. Can you hear me? Okay.
Yeah, go ahead.
It is an honor and a privilege to be here, and I want to thank the Ozisik family for making this possible. I have not had a chance to personally meet Necati Ozisik, but I think there are few in the heat transfer area who have not learned something in sort of graduate level heat transfer, some of the mathematical techniques and so on from his books. And we are all indebted to him. And so I consider this a great privilege to speak at a series named after him. So I'll be giving you kind of an overview of research in the heat transfer area that affects a variety of human essential needs. And the title reflects that. But first, when you come across names like this, yes, of course, there are the research accomplishments. Yes, of course, there are the teaching accomplishments. But the things I want to point out are that he helped his students become leaders. He helped his students become leaders. A kind and thoughtful man. Advances in his profession and developing the next generation of engineering leaders. This is where people leave their legacy, and I think the entire community is indebted to him for what he has done. And then I'm in some very good company here. The first here is Renato Cota, one of my very good friends. He has likewise done wonders for the Brazilian heat transfer and two-phase flow community, and just a very warm and friendly and welcoming person who has helped many, many people. And I would be remiss if I didn't mention what Professor Deluria has meant to me. You may not know that I actually took senior design from him when I was an undergraduate at IIT Kanpur, and he was a faculty member there. In his last year there, he taught me senior design, and he's been such a friendly presence to every young heat transfer engineer throughout the country and throughout the world, and these are the kinds of people that further the field. And so it's we work, we rely, and we climb on the shoulders of these kinds of people to continue their legacy. So a little bit about sort of make them undergo certain processes like phase change, absorption, adsorption, and so on and so forth, to come up with these end users with the overall sort of umbrella of decarbonization through sustainable thermal energy utilization based on an understanding of heat and mass transfer in single and multiple component fluids. And so today's talk, I will kind of highlight these areas where first I spend just a little bit of time talking about some insights in heat transfer that we have gained through research on the fundamentals of fluid flow and heat and mass transfer. And then I'll give you examples of where we have applied those insights to solve everyday challenges in life. So research like this doesn't happen in isolation. These are some pictures of my lab, just to give you a flavor of the sort of large-scale, boilers, chillers, and so on that we use, environmental chambers as the research infrastructure. And then these are some of my test facilities that we have built over the years with the help of students, two-phase flow facilities, heat pump test stands, and so on and so forth. You don't need to look at that in detail, but I think you can get a visual idea of the kinds of experiments we run. So let's talk about some fundamental insights. The key driver in research over the past few decades has been you want to make sure that you get a lot of heat transfer. And for that, these are the only three levers you have. Quite often, the delta T that's available is assigned to you. That comes from the problem. And so the only thing you can play with is the heat transfer coefficient or the surface area. So you must provide more area, must provide a higher heat transfer coefficient, and then whatever delta T there is, try to use it better. And so when you go to the micro scales, you do get high heat transfer coefficients, and you also get high surface area to volume ratio. And so you address those two needs. Also, another hidden advantage is that many working fluids in many applications are either expensive or hazardous or so on. And so when you go to these small scale geometries, then the amount of fluid that you need decreases. And so to take advantage of these, you need to understand the fundamentals of this phase change heat and mass transfer, and I'll just give you a very brief glimpse of that. So many years ago, we did these condensation experiments at very high pressures. These are like 1,000 psi, 1,200 psi type of pressures, which nobody had done before, because it's very hard to visualize while you are at those pressures and while condensation is going on. So we developed some interesting techniques to do that, which I won't go into, but we were able to identify the different types of flow regimes. Previously, the work had been on just air-water mixtures, all sort of being extrapolated to these high-pressure fluids, but that extrapolation doesn't work well, and so we were able to identify what the regimes were and where the transitions happen. And so these phenomena depend upon things like mass flux, the vapor fraction, the phase velocities, and the liquid vapor phase distribution, and so on. And so we studied a variety of sizes and shapes, understood the effect of miniaturization, understood the effect of tube shapes, and so on. And then we were able to come up with idealized models. So if it is intermittent flow, for example, it's one big bubble that is being followed by a slug, by another bubble, and so on. So we calculated or we modeled the pressure drop due to this liquid phase, the vapor liquid shear here, and then the expansion and contraction that happens as this liquid has to sort of squeeze itself into this space and then expands again. So once you consider the sort of underlying mechanisms and you attribute the pressure drops to that, you can then say, okay, at these different conditions, these different mass fluxes and qualities for different diameter tubes, this is the amount of pressure drop that happens, and it is due to these three contributions. Once you do that, you go from what used to be available in the literature, pretty big scatter in predictions, to a much better prediction of these kinds of quantities. But there is not just one fluid that you work with in engineering. There are fluids that operate near critical pressure, that operate at very low reduced pressures, and so on. And so over the years, we've done work on condensation in horizontal and vertical tubes, larger tubes, microchannels, mini channels, and so on. And then a variety of orientations, different fluids, fluid mixtures, and so on. And then we collected a whole bunch of data. The reason why these different types of fluids become challenging and important is they are not very similar at all. Their fluid properties can be significantly different. For example, if you look at the density ratio of the liquid phase to the vapor phase, it can go from 845 down to 11. And so these are very, very different fluids. So studying one fluid and thinking that it applies to the others doesn't work. Similarly, surface tension, air water is 38.1, whereas propane is 4, and so on. So when you study these wide ranges of fluids and their mixtures, you have to be able to come up with models that apply to all of these. Similarly, they operate at the temperatures of interest, they operate at very, very different pressures. So something like this can go all the way up to the critical pressure. Something like this is, very, very low in the vapor dome. Similarly, the vapor dome itself, the shape looks very, very different. Some of them have very small HFG, some of them have very small latent heat of vaporization, some of them are very wide, and so on. So our quest over the years has been to come up with some universal models that apply to all of these. And so again, not just flow visualization, but then sort of tracking the interfaces very carefully and figuring out the void fraction, figuring out where the liquid will be and where the vapor will be. That helps you develop models in a dynamic way of the pressure drop and the heat transfer. So this is what we use for those models. And then for something like 3,500 data points or so, wide range of fluids and mixtures and so on, we were able to come up with models that account for these phenomena quite well. We have come up with some analytical techniques also, where this is the progression of condensation in a square tube. Square tubes are important because what happens is, due to surface tension, the liquid kind of pools in these corners, and so the thermal resistance in these regions decreases, and you get some very good heat transfer in those regions. And so these tubes, so with these kinds of analyses, we've been able to help people understand what shapes are optimal for which application. Supercritical fluids are very important these days for power plants, for refrigeration and air conditioning, and so on. Basically, people have done a lot of research in this area, but then we focused here. And you can see that the fluid will change from a gas-like behavior to a liquid-like behavior here over a very small temperature range. And the specific heat spikes over there, and the density changes suddenly from a very low value to a very high value, and the specific heat is spiking here. So we were able to measure and model those spikes in heat transfer coefficient and the sudden change in pressure drop from these high values as a gas to low values as a liquid through our careful measurement techniques as well as modeling techniques. Condensation does provide high heat transfer coefficients, but you can imagine that the vapor comes in as a high speed, high velocity vapor, and so the heat transfer coefficients are high, but as it condenses, it slows down because it's becoming more and more liquid. The density is going down, the density is going high, and the whole is just a stagnant pool of liquid. And I'll show you this here. You see lots of high velocity, lots of shear, and so on, and then it is kind of getting stratified. And so sometimes, as you progress all the way down to the end, the heat transfer coefficients here can be even lower than single-phase heat transfer coefficients. And so people have tried to enhance heat transfer processes by sort of throwing in some one-thing-fits-all type of technique. But we said, can we come up with some tunable techniques so that we apply the enhancement where it really matters? And so we came up with this idea of using Helmholtz resonators, where there is an acoustic actuator, and it creates some pulsatile flow here, and we match it to the resonance of the geometry. And by doing that, if this is the baseline flow, by actuating it, so this is the baseline flow, by actuating it, you get that kind of an agitation, which gives you very high heat transfer coefficients. And what this does is that tail end of the condenser that usually takes so much surface area to accomplish that condensation, you reduce that size. So whereas the heat transfer coefficient would be high at high vapor qualities, if you don't do this, it just keeps going down, and this is very hard to accomplish. It takes a long tube to make this condensation happen, but if you, in this tunable way, enhance the heat transfer coefficient, you keep it high, and you reduce the condenser size. So that's just one example of an enhancement technique. Lately, AI, ML techniques and additive manufacturing have come in. How can we exploit that? Well, if you have traditional manufacturing processes, if you put in a tube, it's generally a one diameter, one cross-section tube. And so this phenomenon we're talking about where the heat transfer coefficient just decreases because it's slowing down, it hurts you towards the end. So with additive manufacturing techniques, we came up with this idea, and we have applied for a patent for this, where we progressively decrease the diameter of the tube, the number of the tube, we increase, and then we put these hollow baffles here where that condensed liquid is taken away so that that additional thermal resistance goes out of the picture and you're left with this high, fast-moving fluid. And then we've optimized that using AI/ML techniques. So we brought those two ideas into play to come up with substantial reductions in the size of the condenser. Now, a little bit about external flows. We did this work a long time ago. When you have heat transfer, there are two fluids. There's one inside the tube, there's one outside the tube. And if you look at falling films, this is what they look like. At the time we addressed this problem, people used to think that these are just sort of smooth films, circumferential films over tubes. They didn't account for all of these phenomena. So we first said, okay, there's a drop that develops, it stretches into a filament, it breaks down into small droplets and so on. And then when it crashes onto this, it creates these waves here. Then the waves propagate sideways, and then they collide, and then there's a new spot for the next fluid to flow, and then some of these fluid droplets, due to surface tension, don't even integrate into the flow. So you need to understand all of these to come up with heat transfer models for this. And here's our experiments, and then we came up with some computational work that is able to replicate all of those, the formation of the droplet, the extension into the filaments, the breakdown into the small droplets, and then the saddle waves that form at the bottom of this. So this helps you design things like shell and tube condensers and absorbers, desorbers, and so on. You see the waves that are forming. That was fluid flow. This is heat transfer. As long as it stays in contact with the tube, which is being cooled, it stays cold. When it starts absorbing more vapor, it heats up, and then when it falls, then again it cools down. So a fully resolved three-dimensional analysis of this in time to understand the heat and mass transfer processes. And then they give you design insights. So you can say, well, I want to put more surface area. I want to stuff the thing with much more tubes, or I want to flow much higher flow rates because high flow rates is high Reynolds numbers and so on. But then this is what happens. It forms these thick films, and then they don't get a chance to develop into those droplets with surface area and so on. So this also serves as a nice guidance of what optimal designs are. And then you also have to worry about how to distribute the fluid. You don't want these kinds of situations where a lot of the heat transfer surface area is dry because it's not participating in the heat transfer process. And so we came up with different distributor designs and so on to make sure that the fluids are being distributed properly. Another simple way of enhancing heat transfer is to throw in a few ppm, parts per million, of surfactant. And you can see without the surfactant, this is the flow, and with the surfactant, that's what happens. Again, you get plenty of enhancement, and you can reduce your component sizes and so on by doing that. Okay, so that's so much for the a glimpse of heat and mass transfer. Now, the rest of the talk, I'll mention a variety of applications. So one of the sort of hot topics, pun intended these days, is heat pumps. Well, what is a heat pump? Heat wants to go from high temperatures to low temperatures. But the objective of a heat pump is to make it do the opposite. Okay? So heat wants to do that. Our goal in a heat pump is to do that. Okay? And so that's where the challenge lies. Now, this is a vapor compression heat pump where you put electricity to move the heat from low temperatures to high temperatures. There's other routes, namely sorption, where you can actually provide heat as the motive force, and you can achieve cooling using that, you can achieve heat pumping using that, and so on. And in many parts of the world, there is no reliable electricity grid, and so you can use local waste heat, biomass, solar, and so on to do this heat pumping. And so we've devoted quite a few years into this. The principle of operation is this. This is your standard household refrigerator or air conditioner. You put in a compressor, you compress the vapor to above the ambient temperature, it rejects the heat, it expands across a valve. There's an evaporator which does your cooling for you and comes back. Well, this needs electricity, and all the vapor compression fluids these days are being banned because of their global warming potential and so on. So you replace that with a bunch of heat exchangers, and you only need a small pump that consumes maybe 1/100th of the electricity that a compressor would. And so you supply whatever heat you have available, whether it is natural gas or solar or waste heat or whatever, you use that as the heat source, and you boil off the refrigerant from here, you condense it, you expand it, you evaporate it, just like in a regular cycle, and then you mix it back into the absorber, and now you're pumping a liquid, not a vapor, up. So this is versatile, and the working fluids don't have any global warming potential and so on, but you have replaced one compressor with 3 heat exchangers, and that, for things like residential applications, that used to be a challenge because that's much more surface area needed and so on. But we worked on miniaturizing these using our insights into heat and mass transfer that I presented earlier. And so, for example, through our insights into tube side microchannel flow and falling films, we came up with this concept many years ago, where you pour some dilute liquid down this crisscross matrix, and due to that crisscross nature, there's plenty of mixing, a lot of absorption happens. You send the vapor from below to the top, and the vapor gets absorbed, and the heat of absorption is sent through these tubes, these microchannel tubes with high heat transfer coefficients, to result in a fairly small package, 5 inches by 5 inches by about 12 or 13 inches here. You put 4 of these things together, and that gets you a heat pump. Okay? And it can do both absorption and desorption, evaporation, condensation. And then later on, we came up with a challenge. Why not build a heat pump that is the size of a textbook that we follow for our undergraduate classes? And this was the PhD thesis of one of my students. And the way this works is we take these 0.5 millimeter thin sheets of metal, and then we etch about 250 microns passages. And so one sheet has all the components of a heat pump. So you boil the refrigerant, you purify it, you condense it, you do some recuperative heat exchange, you do the evaporation, the absorption, and then send it to another recuperative heat exchanger and so on. So of course, one sheet can only do a small amount, and then you stack as many sheets as you want in a modular fashion to come up with a heat pump. So this heat pump, the size of a textbook, was able to do about 350 watts of cooling simply using waste heat. And then we expanded it to residential heat pumps. To this we developed for the military establishment where people were going to Iraq and Afghanistan and places like that. And you know, to carry fuel there is very, very expensive, and people are losing lives delivering the fuel. And so whenever you burn 1 unit of fuel, you want to use it fully. So they were generating electricity using that diesel fuel, and then we took the exhaust, and just using the diesel engine exhaust, we were able to run this, and basically the cooling was for free for cooling the tents and so on and so forth. Here's a water heater, your residential water heater in your homes and basements. By putting an absorption heat pump like the one I showed you, just on top of the tank of your storage tank in your basement, you can put in 1 unit of gas and get about 1.7 units of heat due to the heat pumping. And so your gas consumption goes down significantly. So these are some of the innovations that heat pumps can help you do. And then some of those pictures I showed you were using expensive processes like photochemical etching, diffusion bonding, and so on. So then we came up with low-cost fabrication by doing stamping, hydroforming and stamping, to come up with these plates that were very similar to what I showed you before, and then we would braze them rather than diffusion bond. And brazing is a well-known process in the automotive industry, for example. Microscale heat exchangers don't just mean small, tiny things. It is the microscale heat transfer phenomena that we can apply to very large systems. So this is an aircraft carrier, for example, where it has something like 300 megawatts of heat input, and 200 megawatts of it goes away. That exhaust heat we use to run an absorption heat pump system, and then we coupled it to a vapor compression system, a CO2 vapor compression system, to use 200 megawatts of heat to produce 90 megawatts of cooling at 5 Celsius, and then 50 megawatts of cooling at minus 40 Celsius for some challenging cooling needs by using only about 23 megawatts of electricity. The way we did this is by using these flat tubes with microchannels in them. We would condense CO2 inside. CO2 is an excellent working fluid, and when you use microchannels, the heat transfer coefficient is very high. Falling film water has very high heat transfer coefficients, and both are isothermal processes, so with just a delta T of 3 degrees, we were able to deliver 40 megawatts across a fairly small package. Okay, one of the big challenges these days is data centers. They put out a lot of heat. What do you do with this heat? Well, this is very mild heat. It's a challenge, but it's only coming out at 50 Celsius and so on. Is there something you can do? Well, this is the state of the art. This is what happens. To be able to provide 200 kilowatts of critical load, you have to burn fuel to come up to put in this much thermal energy. This much goes to waste. And then you have to run a vapor compression cooling system at a COP of 3.3 so that then you can provide this. But there's a lot of waste here. You're throwing away a lot. Can you do something with this? Well, if you have on-site power generation, then you can use that waste heat from that power generation, and you can run this double effect absorption system to get free cooling from that. Okay. On top of that, that waste heat, that mild waste heat, 50 Celsius waste heat, you can use something called a heat transformer, and you can upgrade that heat from 50 Celsius to close to over 100 Celsius, and you can sell that heat because 100 Celsius heat is useful. You can do laundry, you can supply a hospital with sterilization facilities and so on and so forth. And so this is what the balance becomes then. So then you have this waste heat, and you use this to generate your cooling, and then here you use a heat transfer to provide upgraded heat. So you're getting two nice end users, and this with the vast amounts of electricity that is being used for data centers. These are some ideas that will reduce the overall footprint, energy footprint of data centers. And we can, whereas the system efficiency may be 32, we can enhance it all the way to about 41%, a significant improvement. We have an ongoing project on integrating heat pumps with thermal storage. Thermal storage is a big deal because most of the renewable energy sources are intermittent. And also there is another driving force most power plants have certain peaking characteristics, right? The demand has a certain peaking characteristic, and if you exceed that, you have to build new power plants. If you can shift that load somehow, then you don't need to put in new power plants and so on. So here's a typical vapor compression cycle, and we couple it with a thermochemical storage material where the reject heat of the condenser goes into this adsorbent bed. And so that adsorbent bed is what stores that heat for you to be able to use it later on when you really need it. And so then through this combination of charge and discharge, when you have excess available, you charge it and then you discharge it later on to supply your need. And this can be done both for heating and cooling. And we've done some models of the system where we track the charging, the storage when you neither are charging nor discharging, and then what happens later on when you're discharging it. And there are some significant advantages in CO2 emission reduction, peak power reduction, and so on. If you talk about thermal storage, well, then you can talk about electrical storage too. Batteries are a big deal, right? And most batteries have this kind of a profile. You know from using laptops, phones, and so on that they get hot. Well, they get hot, and also they get non-uniformly hot. Inside it is very hot, outside it is a little bit colder. Most cooling techniques just send some cold air on the surface, or at best some jackets of cooling water on the surface. Yeah, that does do some cooling, but that exacerbates this peaking temperature profile. So the center of the battery stays really hot, and then there's big temperature gradients, which are not good for the health of the battery because it causes differential corrosion and so on and so forth. And also the depth of discharge, the battery thinks when one part of the battery has discharged, it thinks, oh, it's done, there's no more left. Well, there is a lot left, but you're not able to access it because of this temperature gradient. So we came up with this idea of integrating microchannels with the current collectors so that we are providing cooling at the source, and then you take that heat and then you send it like in a thermosiphon. So you boil the refrigerant at the right pressure due to this heat supply, and then it goes up, and then you cool it with a fan. And so we're able to get very uniform temperatures and extend the life of the battery as well as the depth of discharge of the battery. And then we also studied abuse events. There are short circuits. Every time you fly in a plane, they say take out your lithium batteries and so on because they're a fire hazard. But this is what happens. There's a short circuit, and then we've been able to predict how this spreads, and this can go to thermal runaway very, very fast. And so we have some predictive tools to model that, and then we can come up with mitigating techniques for that. Okay, some research that Sajjad has been doing also. We did a program of clothing, another essential human need. You want clothes, and you want dry clothes that don't smell. And so you have to dry the clothes, but the clothes drying process is a highly inefficient process with a lot of energy just being thrown away. And in fact, the temperature time profile looks like this. There's this sort of the preheating when the clothes are being raised to the saturation temperature. Then there's the evaporation phase, and then you have to account for the moisture that is deep in the textile. And so you have to heat it to an even higher temperature, and then there's a cool down. And so a heat transfer engineer like me looks at this and says, hey, there's a lot of nice delta T's separated in time. Let me use the heat from one portion, one part of the cycle, to heat up the other cycle. And so we did a variety of these, and we studied moisture transfer at the textile level, at the drum level, and system level. And we came up with these enhancements. Some first recirculation. Well, you can't just recirculate that exiting air because it's wet, and you took a lot of energy to take the moisture out. You can't feed that back in. So then we did recuperation, And then we put in a bunch of silica gel beds to store that energy and use it later on. And then we also put in an adsorption heat pump, and we are able to improve the efficiency substantially. And this is actually the picture in my lab. This was my PhD student's test setup. Okay, another major topic these days, water. Some people say water is the new oil, water scarcity all over the place. Well, when you take a shower, when you wash your dishes and so on, there's a lot of nice hot water that's being thrown away. Okay. So we came up with this idea that, well, we have been developing absorption heat pumps for a long time. It's providing space conditioning. Can we use it to do double duty? Can we also use it to purify that water? So instead of that closed loop that I showed you, if you have an open loop and you pick up that collected water, it goes through a double distillation process. In the evaporator, it is evaporating, so therefore it gets cleaned up to some extent. Then when it goes up to here, goes to the bezover, it gets further distilled, and so you get pure water here. And so this is another student's PhD thesis where he proved that we can get clean water, not to the potable extent, but for many other household users by doing this process. We have also been working with the largest aluminum industry in the world. Whenever you drink a can of Coke or Sprite or whatever, remember that can, it's a very, very energy intensive process. And when you're making an ingot, an aluminum ingot, and these are many stories tall, I actually visited these plants, you are basically pouring a bunch of water around this liquid metal to solidify into an ingot. Okay, that's a big energy intensive thing, but also there's this water that's evaporating when you pour it down there, and that water just goes away. And so first, we estimated exactly what's happening. These are the temperature profiles inside the ingot, and then how much of it is going to sensible cooling, and how much of it is water evaporating. And then we proposed some ways of capturing the water in the plant so that it's not just being thrown away. And we demonstrated that you can, there's something missing in the slide, but significant water savings. Okay. Another major energy consuming industry is gypsum wallboard manufacturing. You see wallboard everywhere. That's a very, very energy intensive process because gypsum has to be calcined, and then it's broken into small, fine particulate matter. It is made into a slurry. That slurry is what forms these rectangular boards, and then you have to get rid of that water. Well, when you're doing this calcination process, usually you just sort of do a gas-fired calcination. When you do gas-fired calcination, there's a lot of hot air going there, and then hot exhaust. That hot exhaust is being thrown away. Secondly, it's a non-uniform heating process because the outer raw material gets heated, burned, and then the inner part still doesn't quite do the calcination and so on. So we suggested that we'll do basically like your household microwave oven, electromagnetic radiation to do this. Electromagnetic radiation is a volumetric process, so the heat doesn't have to go through these conduction pathways and so on. And so it saves a lot of energy because there's not really much exhaust. And then you have this advantage of uniform. And then when you have this uniform heating, then the particles are of a uniform distribution. So the amount of water that you put in for making that slurry and to evaporate it also goes down. So we demonstrated 63% energy and 50% water savings in these processes by doing that. A couple more topics and then I'll stop. Carbon capture, of course, is a very, very important topic. We worked with colleagues in chemical engineering to have these hollow sorbent-loaded crystals in a polymer matrix. And then when you take exhaust gas from the power plant, it goes in and gets absorbed, the CO2 gets absorbed in here, and the heat of adsorption is taken away in these 300 micron channels. And then once you've collected that CO2, in the next phase, you send hot water through it, and then that CO2 is desorbed, and you pick it up and you sequester it. Now, of course, so this is the process. The flue gas comes in, it gets absorbed, and then the captured CO2 is released. And so we did, particle level all the way to overall plant level analysis of this. And in the process of carbon capture, you have to be careful not to put in new energy. So in a power plant, there are enough sort of medium temperature heat sources. And then if you use what is called the thermal wave technique, where as the heating goes on, one portion of this bed is hot, and then it's cooling down. You chase this wave, you pick up the heat from that, store it for the next phase. So the external new heat that you need to put in is very, very minimal. And so we showed that you can get some very high capture efficiencies and very high purities by using this kind of a process. Power plants consume a lot of water. I don't know if that usually comes to your mind. Of course, it consumes a lot of fossil fuels, but it consumes a lot of water because the cooling towers are putting out a lot of just water going out there. And so there has been a recent push to try to reduce the water used in power plants. And so the idea is, instead of using cooling towers, can you enhance the air side heat transfer in a condenser so that its performance is approaching that of something in a cooling tower? And so we came up with this idea of these fluttering reeds, just thin mylar sheets that you insert into the fins of the condenser, of the air-cooled condenser. And then this is, so with a colleague, Ari Glazer, and I and his student and my student, we worked on this, and this is what the fluttering looks like. And then we did some CFD analysis, and we also did a lot of experiments. My student finished his PhD on this last year. And we showed that significant improvements in the heat transfer are possible, so you can reduce the amount of water that you need for power plant cooling. Microchannels can be used also for nuclear reactors. This is a project, a fairly large project with multiple universities, and my role and my students' role was to come up with these microchannel heat exchangers for the primary to secondary cooling. So this would be the reactor core, and in what is called the downcomer, we insert an assembly of these microchannel heat exchangers, and this way the containment size and so on goes down, and you are able to really make these overall, the nuclear envelope, much, much smaller. Then there are other modern concepts for nuclear reactors that are coming up. This is a high temperature gas cooled reactor where the advantage is that it produces a lot of process heat too, so you can co-locate them to do process heating, which is very difficult to decarbonize. Very high temperature heat is difficult to decarbonize. So you can get double duty out of nuclear reactors. And this is actually some inherently safe features. We did transient modeling of this to figure out what happens in a loss of coolant accident and so on, and showed that basically it was inherently safe, that the temperature would never exceed safety limits. Likewise, there are these molten salt reactors these days, and another student just finished his PhD on this, where again the fuel is the triso fuel, and then this is the fly coolant. Again, some transient analyses of what happens when there is an accident, and we showed that the reactor cools down very safely with no threat to anyone with these molten salt reactors. Finally, one of the most important human needs is food. And you often hear about countries, poor developing countries and so on, not having enough food. Well, quite often they actually do have enough food. It's just a question of preservation. If a farmer wants to sell, fruits and vegetables and so on, takes it to the market, these are usually very hot climates, they don't last very long. If you don't sell it that day, you just basically it rots. If we can even increase the shelf life by a few hours, 12 hours, 18 hours, then you get 2 chances, 2 days to sell this stuff. And so we've been working with a company to build adsorption cooling systems where we use chemisorption processes with very high energy densities, where local biomass, cow dung, twigs, and so on is used, wood chips, coconut fiber, and so on. And we use that to run this adsorption cooling system that looks like this. We do the biomass gasification, and we do this, and then we cool that shed so that the produce can last just a little bit longer, and we've also applied this for milk. And so these have been implemented all across India, and that's another way to help farmers' livelihoods as well as reduce the food shortage. And it has other advantages where the smog and so on can be reduced because you're not putting in new CO2 into the system, and you get, combat the food shortage and so on. So this is my group, and I want to in particular point out this guy here, and Sajjad knows him, Eddie Ferreira. Is your product. Thank you, NC State, for giving me the opportunity to advise him. He's doing very well. This was last year. This guy graduated, and this was at his graduation. And so what our research hopes to do is to provide food, water, clothing, shelter, comfort, and energy to the world, one cubic meter at a time. Thank you very much.
Thank you, Srinivas. We have time for questions.
Thank you for the great talk. I have a question regarding heat pumps and the current push towards having refrigerant blends. So there were like initial slides with a lot of fundamental studies on phase and heat transfer and the pressure measurement and all those things. So what do you think the current, there are a lot of challenges regarding low GWP refrigerants and blends. So what kind of fundamental research would be relevant in this scenario, like, to understand a lot of these problems with
Yeah, the low GWP refrigerants is a very, very important topic, and there are several different routes that people are using to address this. Like you implied, many of the sort of conventional refrigerants have high GWP, and so people are either looking at mixtures, or in Europe, for example, propane is being used as a refrigerant. Now, people are scared of propane because of its flammability, but through advances in miniaturizing heat exchangers and so on, the amount of propane that you need can be reduced quite significantly. And if you use what's called a hydronically coupled system, the propane can be outside the house. It doesn't need to be inside the house. So that's one way to address this. Then there are these not-in-kind, I don't know why they call it not-in-kind, but it's basically non-vapor compression systems where there's magnetocaloric, elastocaloric, and so on, different techniques showing up. And then, of course, the absorption systems that we have been working on for a long, long time, and they have zero GWP. So there are many different ways people are coming up with reasonable replacements, but as I have seen, when I was a student, R12 was a big deal. Then it became R134A, then R22, R410A, and so on. All of these eventually, there's some problem or the other with them. And so either natural refrigerant or CO2 is another very good refrigerant for heat pumping purposes. So it's a wide range of studies that can be done to develop this further, and I don't think it will be one solution. So for commercial chillers, for example, ammonia is an excellent refrigerant. For residential applications, it will be something different. So it's a wide range of options that are available.
Great talk. Can you talk about maybe some of the challenges you've had to overcome in helping people adopt some of this technology and get it to market? That's always the hard part, isn't it?
Yes, yes, yes. We would like to have been more successful in getting these technologies implemented. In the US, the biggest driver is first cost. And first cost is hard to beat because people, their horizons are only 6 months or a year at best, and so they're looking for that payback. So we have come up with, as you probably saw, it wasn't just heat transfer enhancements, but we tried to come up with low-cost fabrication processes and so on. So that's been one approach we have used. Another approach is there are wonderful systems already in place, like a vapor compression system has been optimized over more than 100 years. It's a wonderful machine. And so you have to displace that with this sort of nebulous concept of climate change and global warming and so on. There's a lot of resistance to that. Furthermore, if you introduce technology that is very different from current distribution channels, you have to have vendors and distributors and HVAC technicians and so on who have to be trained to come up with something new. And these are often multiple trades. The person who's doing the plumbing is not the one who's doing the HVAC system and so on. So these are some institutional barriers that we face. So what I have tried to do is I've tried to sort of start in kind of the reverse way of how most academic people work, where I look at first the customer's needs, identify the challenge, and then develop the technology or the fundamental insights. It's usually backwards in my case, and it's been helpful. What happens is when you eventually come up with that new technology, you know that it inherently satisfies those needs. So that's the approach I use. I hope you have answered at least conceptually what our approach is.
It's good for the future entrepreneurs in the audience.
Yeah, it's not, there's a saying, you may have heard it, to a person with a hammer, everything is a nail. So I don't try to push my hammer. I want to understand whether, first of all, it is a nail or not, and then find the right tool for it.
Great talk. You talked about the data centers,
Yeah.
and I wanted to, can you explain the process of heat transformers?
Very good. Maybe I can go to that slide.
Okay.
Heat transformers are not something that I came up with. They have been around, the idea has been around for a long, long time. So you saw my schematic on heat pumps and so on. A heat transformer is essentially a heat pump running in reverse. And the way it works is like this. So whereas you would have the heat input at the high temperature end here you have the waste heat source down here. You put in the waste heat here, you put in the waste heat here, and then it goes through the condensation and the evaporation process here, and then you get the upgraded heat here. So you run this cycle kind of in reverse. There are a few other nuances, but that's kind of what's happening. It is essentially an absorption cycle, but run in a way that it is taking low temperature heat and increasing. Now, I want to make sure I clarify that you can't take 100 kilowatts of 50 Celsius heat and put out 100 kilowatts of 100 Celsius heat.
Yeah.
There is an efficiency, and we've shown that the efficiency can be approximately 50%. So 100 kilowatts of 50 Celsius heat will give you 50 kilowatts of 100 Celsius heat, which is a pretty good deal.
Yeah.
So in that process, it's not the silt or the carbon that is the issue. Sometimes it is the competitive absorption between carbon, between CO2 and say things like water vapor and so on. So you try to do some filtration upstream of it. There is never any, so we are not talking about soot and things like that. That is gone well before it comes there. But you are right, there is a challenge of competitive adsorption, and so we try to account for that by putting in the right mix of adsorbents and so on. There are zeolites, there are many other materials that you can use, and we've done some models to minimize that issue. But yes, you have identified an important issue.
One more question.
Thank you, Professor, for the great talk. So, I had a two-part question about this. The first one was when we were talking about the evaporation of external flows. The video demonstration showed a liquid bridge forming between the top tube and the bottom tube. Does this liquid bridge play any particular role? If it does, would it be better to create some coatings on these copper tubes to enhance the duration of the stability of the liquid bridge? And if it does not, would it be better to have a coating that would help in a faster detachment of this liquid bridge?
Yeah, so there are evaporation processes and there are condensation processes, and the needs are different for both of those. Coatings are, in fact, important because you want good wetting of the surface. Okay, you want it to be well wet so that you're not leaving these dry patches. The role of the filament, so your question is two questions. The role of the filament, droplet, the filament, and so on is in the application I talked about. We are actually talking about absorbing vapors into a liquid stream. And if that liquid goes into this filament and becomes droplets and so on, usually I have another slide right after that to show this, but essentially it provides, for the same volume of liquid, it provides more surface area to volume ratio, and so it provides more surface area for that vapor to be absorbed into that. So the role of the liquid bridge, the breakup of the bridge and so on is more important when you're talking about coupled heat and mass transfer processes, like one species absorbing into the other. As far as coatings are concerned, there are coatings and then there are surface modifications too. For example, in this case, those surfaces were sandblasted so that they would be wet and no area of the tube would be dry and not participate. With coatings, of course, that's a whole new field of hydrophobic, hydrophilic, and so on. You can do all kinds of patterns to make sure that the fluid is being directed in a certain way and so on. But it is not a universal answer. So for evaporation, it will be one, condensation will be another as well.
I have a question. You talked about liquid as an option, right? To change the liquid to enhance the heat transfer. What about the material of the heat exchanger itself? There's option there that you have explored, and of course the cost is an issue too there.
The material of the heat exchanger plays a role only in some situations because usually the dominating thermal resistance is either in the inner fluid, or if you are rejecting the heat to air, then the air becomes the dominant issue no matter what you do. The more appropriate or practicable answer is to come up with new ways of putting fins and surface enhancements and also agitating the liquid with the air boundary layer and so on. The materials thing becomes important sometimes from materials compatibility issue. So some materials cannot withstand some sort of corrosive atmosphere or something like that. So the materials are very, very important for structural strength, for longevity and so on. But in heat transfer, in many applications, they play a smaller role.
Any other questions? Will you join me here? All right, this is just a token of appreciation for giving us Ozisik lecture. You can go on your middle.
Put your that. Thank you very much. Much appreciated. And then we also have a small for you. Take away. Remember, NC State. Okay. Well, I will definitely. This has been a memorable experience. Thank you. And thank you to the students. And thank you for the Ozisik family for supporting this. Very inspirational. Yeah. Thank you all.
Thank you. Thank you so much.
Thanks.
Very